A globe. Hold it in your mind. Trace the lines of longitude from the equator downward. They converge. At the South Pole, all directions become north. There is no south of the South Pole. The question does not apply. You have reached a place where the concept of further south simply runs out of meaning. The universe, according to one of the quietest and most radical ideas in physics, is like that globe. Its history does not trail back to a sharp edge, a first instant before which there was nothing. The Big Bang is not a beginning in the way a match struck in a dark room is a beginning. It is a point like the South Pole, an ordinary point on a closed surface, where time itself loses the property of before. The cosmos is self-contained. It needs no external cause, no hand lighting the fuse, because there is no boundary in time to stand outside of. The question, what happened before the Big Bang, may be as empty as the question, what lies south of the South Pole. Hello, and welcome to Sidereal. Tonight we are going to follow a single thread, from a wooden desk in a patent office in Bern to the shape of the whole of time. It runs through relativity, through the death of stars, through the discovery that most of the universe is invisible, and it ends at a strange and beautiful proposal about the origin of everything. If you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps the channel, and I'm curious where you are listening from. Leave your city and your local time in the comments. It is one of the quiet pleasures of building these stories, knowing the map of people lying in the dark, listening. Here is the question that will carry us through the night. How can a universe that erupted from an unimaginably hot, dense state, a universe whose galaxies are still fleeing from one another in the aftermath, have no beginning at all? By the time the night is over, you will understand why that question might not apply, and how the road to that understanding began with one man at that wooden desk, thinking not about the cosmos but about light and clocks and what it means to say that two things happen at the same time. Let us begin with the size of the thing we are trying to explain. The visible universe extends roughly 46 billion light-years in every direction from where you are lying right now. Within that sphere, there are something like 2 trillion galaxies, each one a vast city of stars turning slowly in the dark. Our own galaxy, the Milky Way, holds somewhere between 100 and 400 billion suns. These numbers are too large to feel. The mind refuses them, but one fact can settle in the chest and stay there. In the 1990s, astronomers pointed the Hubble Space Telescope at a patch of sky so small it was like holding a grain of sand at arm's length and staring at the sky behind it. A patch that looked, to every previous instrument, completely empty. They left the telescope staring into that darkness for days, gathering the faintest light. And when the image came back, that empty grain of sky held around 10,000 galaxies, not 10,000 stars. 10,000 galaxies, each with its own hundreds of billions of stars. And that grain is one tiny fraction of the whole dome of the sky. The universe is not merely large, it is thick with light and structure at every scale you care to examine, and the deeper we look, the more of it there is. This immensity has not always existed. A little under a century ago, astronomers discovered that the galaxies are moving apart from one another. The space between them is stretching. Run that motion backward, like a film in reverse, and everything draws together, closer and closer, until it converges toward a single point of impossible density, where our equations stop working and the thing we call time appears to begin. This is the hot Big Bang, and it rests on a body of evidence that is genuinely overwhelming. The clearest piece of that evidence fills the sky around you at this very moment. A faint glow of microwave radiation comes from every direction in space. It is the cooled afterglow of a universe that was once opaque and blazing, an ancient light released when the cosmos first became transparent. Its temperature today is 2.725 Kelvin, barely above absolute zero, the coldest anything can be. And it is smooth. It is the same in every direction, to within about 1 part in 100,000. That smoothness tells us the early universe was in an intensely hot, dense, and simple state, uniform almost everywhere. But that same smoothness hides a puzzle, and it is worth holding on to, because it will return later tonight with real force. two regions on opposite sides of the sky, so far apart that light could never have traveled between them in the entire history of the universe, somehow have the same temperature, to a staggering precision. They have never been in contact. They could not have exchanged heat, or light, or any signal at all. And yet they agree. Something must have arranged that agreement before the ordinary expansion took over. Hold that thought. It will not be answered for a long while. So the story seems clear enough. An origin, a point of infinite density, a cooling fireball, the slow gathering of matter into stars and galaxies, and eventually, on a rocky planet orbiting an ordinary star, creatures who can look out at all of it and ask how it began. This is a story with a beginning. The no-boundary proposal says otherwise. It says that the point at the start, the singularity, was never quite as real as a cliff edge is real. It was an artifact of looking at time in one particular way. If you rotate your perspective, using a mathematical technique with the strange name of imaginary time, the geometry of the earliest universe closes up smoothly, like the surface of a sphere, with no edge. The Big Bang becomes a point as ordinary as the South Pole, with nothing before it, because there is no before to be had. The universe is not something that was lit and set in motion. It is something that simply is finite in the past, and yet without any boundary. This is not mysticism. It is a prediction that comes out of combining general relativity with quantum mechanics in a particular way, first laid out by two physicists, James Hartle and Stephen Hawking, in 1983. It has not been proven. It has not been disproven either, and it sits at the far end of a long chain of reasoning that began with a young man who was not thinking about the cosmos at all. He was 26 years old, working at a desk in an office, and he was about to take apart 2 centuries of certainty about the nature of time. That is where we start, not at the beginning of the universe, but at the beginning of the thread, in an office in Bern, in the year 1905. In 1905, Albert Einstein was 26 years old, working as a technical expert, 3rd class, at the Swiss Patent Office in Bern. He had wanted an academic post and had failed to get one. Physics was something he did in the margins of his days. On scraps of paper, he pulled from a desk drawer when his supervisor was not looking, and pushed back into the drawer when footsteps approached. That year, in his spare hours, he published 4 papers. Any one of them would have made a career. The third, received by the journal on the 30th of June, was titled On the Electrodynamics of Moving Bodies. It contained no citations. It referenced no authority. It began with a simple observation, and by the time it ended, the idea of absolute time was gone. For most of human history, time had been understood as a great river, flowing everywhere at the same rate. Isaac Newton had made this formal in the 1600s. Absolute, true and mathematical time, he wrote, of itself and from its own nature, flows equably, without relation to anything external. One tick of the cosmic clock was one tick, wherever you stood and however you moved. Space was a fixed stage. An event had a definite place and a definite moment, and those facts did not depend on who was watching. This matched every human intuition. It still does. When you and I agree to meet at 8 o'clock, we do not stop to wonder whose 8 o'clock we mean. The trouble came from light. In the 1860s, James Clerk Maxwell had unified electricity and magnetism into a single set of equations, one of the great achievements of 19th century science. Those equations predicted that electric and magnetic waves travel through empty space at a specific speed, close to 300,000 kilometers per second. The number fell straight out of the mathematics, with nothing put in by hand. But it raised an immediate and awkward question. Speed relative to what? If you run toward a beam of light, does the light come at you faster, the way a wave comes faster at a swimmer wading toward it? Maxwell's equations said no. They gave the same speed no matter how the source moved, no matter how the observer moved. This was so hard to accept that physicists invented a substance to carry the waves, a luminous ether filling all of space, providing the one true frame of rest. Light moved at its fixed speed relative to the ether. If you moved through the ether, you should measure something slightly different, just as a person walking the deck of a moving ship sees the water pass at a different rate than someone standing on the shore. The experiment to catch the ether was performed in 1887 in Cleveland, Ohio, by Albert Michelson and Edward Morley. They built an instrument that split a beam of light, sent the two halves down perpendicular paths, and recombined them. If the Earth was moving through the ether, the light traveling along that motion should take a slightly different time than the light traveling across it, and the two beams, recombined, would fall out of step. The shift would be tiny, but their instrument was sensitive enough to catch it. They found nothing, no shift. The Earth seemed not to be moving through any ether at all. They refined the experiment, doubted it, and repeated it. The nothing held. Physicists tried to save the ether. Hendrik Lorentz and Henri Poincaré suggested that objects moving through it might physically contract along the direction of motion by exactly the amount needed to hide the effect. The mathematics could be made to work, but the picture grew stranger with every patch. A substance that could not be detected, that offered no resistance to anything moving through it, that nonetheless dictated the speed of light. The ether was becoming a ghost, kept alive only because no one could imagine doing without it. Einstein simply cut the knot. He did not begin with the Michelson and Morley result, though he knew of it. He began with something more like a daydream. He had been wondering, since he was a teenager, what it would be like to chase a beam of light and catch up to it. If you could run alongside a light wave at exactly its speed, you would see the wave standing still, a frozen pattern of electric and magnetic fields, hanging motionless in space. But Maxwell's equations do not permit such a thing. A frozen light wave is not one of their solutions. It cannot exist. And so Einstein drew the only conclusion he felt he could. The laws of physics must be the same for everyone moving at a steady speed, and the speed of light in empty space must be the same for all of them, regardless of how they move. Two simple postulates. Taken seriously, they force a complete rebuilding of space and time. The first thing that breaks is simultaneity, the idea that two events happen at the same moment. Picture a train moving smoothly along a straight track. In the middle of one carriage, a passenger strikes a match. Light spreads from the flame toward the front of the carriage and the back at the same speed in both directions. To the passenger, sitting at the center, the light reaches the front wall and the back wall at the same instant. The two events are simultaneous. Now picture someone standing on the embankment, watching the train go by. To that person, the back of the carriage is rushing toward the place where the match was struck, and the front is rushing away from it. The light still travels at the same speed in both directions, but now the distances are not equal. The light reaches the back wall before it reaches the front. To the observer on the ground, the two events are not simultaneous at all. There is no way to say which of them is right, because there is nothing to appeal to, no master clock, no true frame. Simultaneity depends on your motion, and that is simply how the world is built. And once simultaneity goes, absolute time goes with it. If two observers cannot agree on whether two events happen at once, they cannot share a single universal now. The rate at which time passes must itself differ between observers who are moving relative to one another. The mathematics gives a precise factor. A clock moving past you at 9/10 of the speed of light ticks at less than half the rate of a clock at rest beside you. At 99% of light speed, it slows to about 1/7. Push it closer still, and the clock slows to a crawl. This is not a mechanical fault in the clock. It is time itself, running slow. Every clock, of every kind, biological, atomic, mechanical, slows together, because it is the moment that is stretched, not the machinery. This sounds like an exotic prediction that could never touch ordinary life, but it is confirmed above your head every second of every day. High-energy particles from deep space, cosmic rays, strike the top of the atmosphere and shatter into showers of smaller particles. Among them are muons, heavy, unstable cousins of the electron. A muon, sitting at rest in a laboratory, lives for about 2/millionths of a second before it decays. 2/millionths of a second is nowhere near long enough for a muon, even moving close to the speed of light, to travel from the upper atmosphere down to the ground. By every reasonable calculation, it should decay high in the air, far above our heads. And yet we detect muons at sea level in enormous numbers. They arrive. The reason is time dilation. From our point of view on the ground, the muon is moving so fast that its internal clock runs slow, and its brief life stretches out long enough for it to complete the fall. Consider it from the muon side for a moment. You are the muon now. Your clock feels perfectly normal to you. 2/millionths of a second is still all the life you have. But from where you sit, moving at nearly the speed of light, the atmosphere is not 100 kilometers of air. It is compressed, flattened along your direction of travel, into something more like 14 kilometers. The distance shrinks to fit the time you have. This is the other face of the same effect. Moving objects contract along the direction they move, and so both stories, the one told on the ground and the one told by the muon, end in exactly the same place. The muon reaches the surface. What each of them calls time, and what each of them calls space, are different. The physics they agree on. Einstein's paper laid all of this out with a clarity that made the ether simply unnecessary. If the speed of light is the same for everyone, and the laws of physics are the same for everyone moving steadily, then there is no need for a frame of absolute rest, and no reason to expect Michelson and Morley to find one. Space and time are not a fixed background against which events unfold. They are woven together into a single thing, which the mathematician Hermann Minkowski would soon call spacetime, and different observers slice that single thing into space and time in different ways. The division between past, present, and future is not a feature of the universe. It is a feature of the observer's motion through it. There was one more result, published a few months later, in a short follow-up note only 3 pages long. Its title was a question. Does the inertia of a body depend upon its energy content? The answer was yes. If a body gives off energy, its mass goes down. Mass and energy, it turned out, are two faces of the same coin, related by the most famous equation in all of science. Energy equals mass, multiplied by the speed of light, squared. The speed of light squared is an enormous number. It means a very small amount of mass is equivalent to a very large amount of energy. A single kilogram of matter, if it could be converted completely, would release the energy of a large nuclear explosion, enough to keep a bright household bulb burning for something like 28 million years. The sun does this every second. It converts about 4 million tons of its own mass into light and heat, and it's been doing so for 4.5 billion years, and it still has most of its fuel left. This is why stars shine. Matter, in a real sense, is a kind of frozen energy, and stars are slowly thawing. But for all its reach, this theory had a name that gave away its limit: special relativity. Special meaning restricted. It described observers moving at a steady speed in a straight line, and nothing else. It said nothing about acceleration, and it said nothing about gravity. Newton's law of gravitation, which had stood unshaken since 1687, described gravity as a force reaching instantly across any distance. The sun pulled on the earth pulled on the moon, all at once, with no delay. But special relativity forbids anything from moving faster than light, information included. Gravity could not be a force that leaped across the void in zero time. Something had to give. That was the loose thread Einstein could not leave alone. For the next decade, it consumed him. The answer, when it finally came, would not describe gravity as a force at all. It would describe it as the shape of space and time. The special theory had shown that the clock can run slow. The general theory would show that the clock can bend and stretch, and in the right conditions, fall completely silent. The thought that Einstein later called the happiest of his life came to him in 1907, while he was still at the patent office, still without a university post. The thought was this: a man falling freely does not feel his own weight. During the fall, gravity seems to vanish. If he lets go of a stone in midair beside him, it does not drop away. It hovers there, next to his hand, because it is falling at exactly the same rate he is. Everything falls together, and in that shared fall, the pull of gravity disappears from the inside. This was not entirely new. Galileo had noticed, centuries earlier, that all objects fall at the same rate regardless of their weight. But Einstein saw a principle in it, and the principle was radical. Acceleration and gravity are, at least locally, the same thing. No experiment you could perform inside a sealed room, with no windows, could tell you whether that room was sitting still on the surface of a planet or being pulled through empty space at a steady rate of acceleration. If you stand on the floor and feel weight in your feet, that feeling is identical in the two cases. Gravity, which Newton had described as a universal attraction between masses, was beginning to look less like a force and more like a feature of your frame of reference. This equivalence between gravity and acceleration was the seed. It took Einstein 8 years to grow it into a full theory, and the work nearly broke him. He had to learn a branch of mathematics almost no physicist of the time had touched: the geometry of curved surfaces in any number of dimensions, developed decades earlier by Vera Rubin and refined by others into a tool called tensor calculus. He turned to an old friend from his student days, Marcel Grossmann, now a professor of mathematics, who searched the literature and pointed him toward the right ideas. Einstein wrote to a colleague that Grossmann had saved him, though he complained bitterly that the mathematics was so difficult he could scarcely tell whether it was worth the trouble. He filled notebooks with false starts. He found an approach, worked on it for 2 years, then discovered it was wrong and had to go back. By the autumn of 1915, he was working at a pace that left him exhausted and unwell, racing toward the final equations. The central idea when it arrived was this: mass and energy bend the fabric of space and time around them. What we feel as gravity is simply matter following the straightest available path through that bent geometry. The Earth does not orbit the Sun because an invisible rope holds it. It orbits because the Sun's mass has curved the space-time around it into a kind of valley, and the Earth is rolling along the straightest line it can, which, in that curved landscape, happens to be an orbit. Decades later, the physicist John Wheeler would compress the whole theory into a single sentence: matter tells space-time how to curve. Space-time tells matter how to move. The equations that carried this idea made specific, testable predictions, and the first involved a planet. For decades, astronomers had known that the orbit of Mercury did not quite behave. The point of its closest approach to the Sun shifts slowly around, orbit after orbit, and most of that shift could be explained by the gentle tugging of the other planets. But a small piece remained, about 43 seconds of arc per century, that Newton's gravity could not account for. A second of arc is a tiny angle, 1/3600th of a degree. 43 of them per century is almost nothing. But it was real, it was measured, and it would not go away. Einstein took his new equations and calculated how Mercury should move through the curved space-time near the Sun. The answer came out to 43 seconds of arc per century. Exactly. He later told a friend that when he saw the number, he felt something happen in his chest, a physical shock, and that for a few days he could not work. He knew, in that moment, that the theory was right. The second prediction was stranger and more public. If mass curves space-time, then light passing near a massive body should follow a bent path, because the space it travels through is itself bent. The Sun should deflect the light of stars passing close to its edge. The effect was small, about 1 3/4 seconds of arc for a ray just grazing the Sun's surface, roughly the width of a coin seen from 2 miles away. And there was a clean test built into the number. If you treated light as ordinary particles falling under Newton's gravity, you also got a deflection, but only half as large. Einstein's curved space-time predicted double the Newtonian value. Measure the bending, and you could tell the two theories apart. But to measure it, you had to see stars right next to the Sun, which meant you had to wait for a total eclipse, for the few minutes when the Moon covers the Sun's blinding disk and the nearby stars come out. The man who set out to make the measurement was the English astronomer Arthur Eddington. He was one of the very few people in Britain who fully understood Einstein's work, and his situation during the First World War was delicate. Eddington was a Quaker and a pacifist, and as the war ground on, he faced the possibility of prison for refusing military service. British science had largely cut its ties with German science, and here was an Englishman proposing to cross the world to confirm a theory made by a German in the middle of the war. His colleagues at Cambridge argued that his scientific work was too important to lose, and he was released from service on the condition that he lead an expedition to observe the eclipse of the 29th of May, 1919. A pacifist saved from prison by a promise to test an enemy nation's theory. The irony was not lost on anyone. 2 teams were sent. One went to Sobral in northern Brazil. The other, led by Eddington himself, went to the island of Principe, off the west coast of Africa. They carried telescopes and fragile photographic plates across an ocean, and they set up and waited. On the morning of the eclipse, Principe was covered in cloud. Rain had fallen through the night. Eddington and his small team watched the sky and could do nothing but hope. As the moment of totality approached, the clouds thinned just enough. For a few critical minutes, the sun's darkened disk showed through the drifting cover, ringed by stars. They took 16 photographs. Most were ruined by cloud, but 2 plates showed stars clearly enough to measure. Eddington developed them there, on the island, comparing the positions of the stars near the sun with photographs of the same stars taken months earlier when the sun was elsewhere in the sky. The stars had shifted. They had moved outward, away from the sun, by close to the amount Einstein had predicted. The team at Sobral had clearer weather but trouble with their main instrument, which had been distorted by the heat. Their backup telescope, smaller, produced good plates. When all the measurements were brought back to England and analysed, the 2 expeditions gave deflections that scattered around Einstein's value and away from Newton's. The uncertainties were large. Later observers would sometimes argue that Eddington had been lucky, or that he had leaned on the data he trusted. But the result stood, and it was confirmed many times over in the decades that followed, with steadily improving precision. On the 6th of November, 1919, Eddington presented the findings to a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room was full. The philosopher Alfred North Whitehead, who was there, later described the atmosphere as that of a Greek drama, a sense of fate playing out on a stage. The next morning, the Times of London ran the news across its pages. Einstein, until then known only to a small circle of physicists, became overnight the most famous scientist alive, a status he never entirely lost and never entirely wanted. But the theory carried an implication that Einstein himself could not bring himself to accept, and it was hiding in his own equations from the start. When you apply the field equations not to a planet or a star but to the entire universe at once, they refuse to sit still. Gravity is attractive. Matter, spread through space, should pull itself together over time. A universe full of matter should be either expanding or contracting. It could not simply hang there, static and eternal. That was not the universe anyone believed in. In 1915, the accepted picture was of a cosmos that was fixed and everlasting. The stars moving here and there, but the whole never changing. Einstein shared that belief, and so he did something he would later regret. He added a term to his equations, a quantity he wrote with the Greek letter lambda, and called the cosmological constant. It acted as a gentle outward pressure, a kind of anti-gravity spread evenly through space, tuned to exactly cancel the inward pull of matter and hold the universe still. Nothing in the physics required it. It was inserted by hand, to make the mathematics agree with a belief. Years later, according to the physicist George Gamow, Einstein called it the greatest blunder of his life. Whether he used exactly those words is uncertain. That he came to regret it deeply is not. While Einstein was adjusting his equations to keep the universe frozen, other people were taking those same equations more seriously than he was, and what they found in them was a universe that had been moving all along. In 1922, a Russian mathematician and meteorologist named Alexander Friedmann, working in what was then Petrograd, sat down with Einstein's field equations and asked what would happen if he did not force the universe to be static. He found families of solutions. In some, the universe expanded. In some, it contracted. In some, it expanded, and then fell back, and did it again, oscillating. The cosmological constant was not needed for any of them. Friedmann sent his work to Einstein, who dismissed it, replying that there must be a mistake in the calculations. Friedmann wrote back, patiently, showing the mathematics line by line. Einstein eventually admitted the equations were correct, but insisted they had no bearing on the real world. Friedmann died a few years later, in 1925, of typhoid fever, at the age of 37, without ever knowing that his equations described the universe we actually live in. A few years after Friedmann, a Belgian priest and physicist named Georges Lemaitre arrived at the same place, independently. Lemaitre had studied at Cambridge and at the Massachusetts Institute of Technology, and he was comfortable with both the new relativity and the new astronomical data beginning to trickle out of American observatories. In 1927, he published a paper, in French, in an obscure Belgian journal that derived the expanding universe from Einstein's equations, and then went further than Friedman had. He argued that the spiral nebulae, which astronomers had been watching for over a decade, were actually racing away from us, and that their flight was direct evidence of an expanding cosmos. He even estimated the rate, and because it was buried in a journal almost no one read, it was ignored. Lemaitre had seen the true shape of the universe, and the world simply passed him by. When he tried to tell Einstein about it in person, Einstein reportedly said that his calculations were correct but his physics was abominable. The evidence, meanwhile, was piling up on its own, and it began with a woman whose name belongs at the very centre of this story and is too often left at the edge. Henrietta Swan Leavitt worked at the Harvard College Observatory as a computer. That was the job title given to the women hired to do the painstaking work of examining photographic plates and cataloguing the brightness of stars one by hand. They were paid a few cents an hour and were generally not permitted to operate the telescopes whose plates they studied. In 1912, Leavitt published a study of a particular kind of star in the Small Magellanic Cloud, a faint smudge of light in the southern sky. The stars she studied are called Cepheid variables. They pulse, brightening and dimming in a steady rhythm over days or weeks. Leavitt noticed something that no one had seen. The brighter the star, the longer its rhythm. A Cepheid that took 30 days to complete its cycle was reliably more luminous than one that took 3. And because all the stars in that cloud were at roughly the same distance from us, the pattern revealed their true brightnesses. This was the key that unlocked the scale of the universe. If you find a Cepheid anywhere in the sky and measure its rhythm, you know how bright it truly is. Compare that to how bright it merely appears, and the difference tells you how far away it must be. Leavitt had built a ruler that could reach across space. She received almost no recognition for it in her lifetime. She died of cancer in 1921, at 53, before the full weight of what she had done became clear. A member of the Swedish Academy later began the process of nominating her for a Nobel Prize, not realizing she had already been dead for several years. The prize is not given after death. Her ruler, though, is still in use. The director of her observatory, Harlow Shapley, used Leavitt's method to measure the size of the Milky Way, and found it far larger than anyone had thought, perhaps 300,000 light-years across. But Shapley believed that this enormous galaxy was the entire universe, and that the spiral nebulae were merely small clouds of gas within it. Others disagreed. They argued that the spirals were separate galaxies, island universes, lying far beyond the Milky Way's edge. On the 26th of April, 1920, the two views met head-on in Washington, in what became known as the Great Debate. Shapley argued for one vast galaxy. Heber Curtis argued for a universe of many. Neither man convinced the other, and neither could win, because neither had the one thing that would settle it: a direct measurement of the distance to a spiral. That required finding individual Cepheids inside the nebulae, and no telescope on Earth was yet powerful enough to do it. The telescope that could sat on Mount Wilson, above Pasadena, in California. Its mirror was 100 inches across, the largest in the world, and the man who would use it to end the debate was Edwin Hubble, a former lawyer from Missouri who had thrown over a comfortable legal career to study the sky. He had been a scholar at Oxford, where he picked up a British accent and a habit of wearing capes and smoking a pipe, mannerisms that some of his colleagues found impressive and others found insufferable. He was tall, athletic, ambitious, and certain of himself. He arrived at Mount Wilson in 1919, just as the Great Telescope came into full operation. On the night of the 5th of October, 1923, Hubble took a long exposure of the Andromeda Nebula, the brightest spiral in the northern sky. When he developed the plate, he found what he first took to be 3 stellar explosions and marked them on the glass with the letter N for nova. Then he compared the plate to earlier ones and realized that one of the 3 was not an explosion at all. It was brightening and dimming in a steady rhythm. It was a Cepheid. He crossed out the N and wrote, above it, in a moment now preserved on the actual plate, the word variable, with an exclamation mark. Using Leavitt's rule, he calculated the distance. Andromeda was around 1 million light-years away, far beyond even Shapley's oversized Milky Way. The spirals were galaxies. The universe was immeasurably larger than the debate had imagined. Hubble sent the news to Shapley in a letter, and Shapley, reading it, is said to have turned to a student and remarked that here was the letter that had destroyed his universe. Hubble was not finished. He turned to the spectra of galaxies. The light spread out into its component colours, where dark lines mark the fingerprints of the elements. If a galaxy is moving toward us, those lines shift toward the blue end. If it is moving away, they shift toward the red. This is the same effect that makes a passing siren drop in pitch as it goes by. Working with a remarkable assistant named Milton Humason, Hubble set out to measure both the distances and the shifts of many galaxies. Humason's path to astronomy was unlikely in the extreme. He had started on Mount Wilson as a teenage mule driver, hauling equipment and supplies up the mountain trail. He became a janitor at the observatory, then a night assistant, and turned out to have an extraordinary gift for the delicate, patient work of capturing faint spectra on glass. Between them, the pipe-smoking Oxford man and the former mule driver compiled the data. In 1929, they published the result. The farther away a galaxy was, the faster it was rushing away from us, and the relationship was a straight line. Double the distance, and you double the speed of recession. This is the signature of expansion. Not galaxies flying apart through space from some central explosion, but space itself, stretching, everywhere at once, carrying the galaxies along with it, like raisins in rising dough, each one seeing all the others recede. Hubble's first estimate of the rate was far too high, thrown off by errors in his distances, but the pattern was unmistakable and correct. Run it backward, and everything converges. The universe had a beginning. Lemaitre had been right all along. Einstein, who had resisted all of this and invented a cosmological constant to prevent it, came to Mount Wilson in 1931, met Hubble, and looked through the great telescope. He set the cosmological constant aside. The static, eternal universe was finished. It had been a beautiful idea, and it was wrong. The last great confirmation arrived, decades later, as a hiss of noise no one wanted. In 1964, two engineers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were testing a large horn-shaped antenna built for satellite communication. They were not looking for the beginning of the universe. They were trying to make careful radio measurements, and they were plagued by a faint background hiss they could not get rid of. It came from every direction, day and night, in every season. They checked the receiver, they checked the wiring. A pair of pigeons had nested inside the horn, and the two men climbed in, evicted the birds, and cleaned out the droppings, thinking that might be the source. The hiss remained, exactly as before. Not far away, at Princeton, a group of physicists led by Robert Dicke had reasoned that if the universe began hot and dense, some of that primordial heat should still be around today, cooled by billions of years of expansion to just a few degrees above absolute zero, and detectable as a faint microwave glow. They were building an antenna to look for it. Penzias heard, through a chain of colleagues, about the Princeton work, and telephoned Dicke. Dicke listened, hung up the phone, and turned to the others in the room. "Boys," he said, "we have been scooped." The hiss that Penzias and Wilson could not eliminate was the cosmic microwave background, the oldest light in the universe, released about 380,000 years after the expansion began. When the cosmos finally cooled enough for atoms to form and for light to travel freely, it was not noise, it was the afterglow of the beginning, filling the whole sky, arriving from every direction at once. The two engineers had been trying to clean it out of their instrument. It had been the most important signal they would ever receive. The Big Bang, a name coined in mockery by the astronomer Fred Hoyle, who preferred an eternal universe and never accepted the theory he had accidentally named, had won. The expanding universe, traced backward, pointed to a beginning, and a beginning meant a singularity, a point of infinite density where the equations break down and the theory confesses that it can go no further. But before we can follow the road all the way back to that point, there is a problem we have been carrying since the first minutes of tonight, hiding inside the very smoothness of that ancient light. Most of the universe, it turns out, is made of something we cannot see at all. In 1933, a Swiss astronomer named Fritz Zwicky, working at the California Institute of Technology, turned his attention to a great swarm of galaxies called the Coma Cluster. Zwicky was a difficult, brilliant, abrasive man, prone to calling colleagues he disliked spherical bastards, on the grounds that they were bastards whichever way you looked at them. He was also decades ahead of his time. He wanted to weigh the cluster, and he had two ways to do it. First, he could estimate its mass from the light, count the galaxies, judge how many stars each contained, add it up. Second, he could estimate the mass from the motion. The galaxies in the cluster were moving, orbiting the common center, and the speed of that motion depended on the total gravity holding them together. More mass meant a deeper gravitational well and faster motion. Measure the speeds, and you can work backward to the mass required to keep the galaxies from flying apart. The two numbers should have matched. They did not. They were not even close. The galaxies were moving so fast that the visible matter, all the stars in all the galaxies, could not possibly hold the cluster together. By the light, the cluster should have come apart long ago, the galaxies scattering into the void. By the motion, there had to be far more mass present than anything that shone. Zwicky calculated that the cluster needed something like 400 times more mass than its stars provided. He gave the missing mass a name: Dunkel Materia, dark matter. And then, for the better part of 40 years, almost no one paid attention. The measurement was hard, the numbers were uncertain, Zwicky was disliked, and the idea that most of the universe was invisible was easy to set aside as a mistake in the arithmetic. The idea did not become impossible to ignore until a quieter and far more careful astronomer forced the issue. Vera Rubin came to the study of galaxies in the 1960s and 70s, and she chose to work on a problem that seemed, at the time, almost too safe to be interesting. She measured how galaxies rotate. A spiral galaxy turns like an enormous pinwheel, and Rubin, working with the instrument builder Kent Ford, set out to measure the speed of that turning at different distances from the center. She began with Andromeda, the same galaxy Hubble had used to end the Great Debate, and then moved through dozens of others. The expectation was simple and clear. In the solar system, the inner planets move fast and the outer planets move slowly. Mercury races around the Sun, Neptune crawls. This is because almost all the mass, the Sun, sits at the center, and the pull of gravity weakens with distance. A galaxy, most astronomers assumed, should behave the same way. The bright central bulge holds most of the stars, so the stars far out in the thin edges of the disk should orbit slowly, trailing behind, the way Neptune trails behind Mercury. That is not what Rubin found. She found that the stars at the outer edges of galaxies were moving just as fast as the stars near the center. The rotation curve, as it is called, did not fall off with distance. It stayed flat out as far as she could measure, past the visible edge of the galaxy, into the darkness where there were almost no stars at all. For the outer stars to move that fast without being flung off into space, there had to be a great deal more mass present than the light revealed, and it had to extend far beyond the glowing disk, in a vast, invisible halo surrounding the whole galaxy. She measured galaxy after galaxy, and the answer was always the same. The visible galaxy, the part that shines, is a bright island floating at the center of something enormous and dark, several times more massive, that we cannot see. Rubin was cautious by temperament, and she was careful not to overstate her results. But the results did not need overstating. They were consistent, they were repeatable, and they came from ordinary galaxies, not exotic clusters. By the late 1970s, the weight of her measurements had done what Zwicky's single cluster could not. The scientific community accepted that something was missing. Most of the mass of the universe does not shine, does not absorb light, does not emit it. It makes itself known only through gravity. Vera Rubin never received a Nobel Prize, an omission many of her colleagues considered one of the clearest injustices in the history of the award. She spent much of her later life working to open astronomy to women who had been kept out of it, as she herself had nearly been. What could the dark matter be? The first guess was the most ordinary one. Perhaps it was simply normal matter that happened not to shine. Cold clouds of gas, burned out stars, dim failed stars too small to ignite, stray planets, black holes. Things made of the same protons and neutrons as everything familiar, but dark. This was a reasonable idea, and it was tested, and it largely failed. There are strong limits on how much ordinary matter the universe can contain, and they come from the earliest minutes of the cosmos, when the light elements were forged. The proportions of hydrogen and helium and lithium that emerge from those first minutes depend sensitively on how much ordinary matter was present. The measured proportions match a universe in which ordinary matter is scarce, far too scarce to be the dark matter. Whatever holds the galaxies together, most of it is not made of the same stuff we are. The strongest single piece of evidence that dark matter is real, and not merely a sign that our understanding of gravity is wrong, came from a collision. There is an object in the southern sky, catalogued under a long string of numbers and known more simply as the Bullet Cluster, where two great clusters of galaxies have crashed through one another. When galaxy clusters collide, the individual galaxies, tiny and far apart, mostly sail past each other untouched. But the vast clouds of hot gas that fill the space between the galaxies, which actually contain most of the ordinary matter, do not sail past. They slam together, heat up, and slow down, lagging behind in the middle of the wreck. Astronomers can see that hot gas directly, glowing in high-energy light, and they can map the total mass of the whole system separately, using the way its gravity bends the light of more distant galaxies behind it, a phenomenon called gravitational lensing. Mass warps space, and warped space distorts the images of whatever lies beyond. Here is what the two maps showed. The ordinary matter, the hot gas, was piled up in the center, slowed by the collision, but the gravity, the mass, was not centered on the gas. It had passed straight through and moved on ahead, concentrated in two clumps out on either side, tracking the galaxies rather than the gas. The mass and the visible matter had come apart. Whatever carries most of the gravity had flown through the collision almost without interacting, exactly as a cloud of dark matter should, feeling gravity but nothing else. It is very hard to explain that separation by tinkering with the law of gravity, because there is nothing in the center, where the ordinary matter sits, for a modified gravity to grab hold of. The gravity is out where the invisible stuff went. For many physicists, that image settled the question. Not for all of them. There is a rival idea, proposed in 1983 by the physicist Mordechai Milgrom, that there is no dark matter at all, and that instead the law of gravity itself changes subtly at the very low accelerations found in the outer reaches of galaxies. This approach can reproduce the flat rotation curves that Rubin measured, and it does so with surprising economy in individual galaxies. But it struggles with clusters, and it struggles with the Bullet Cluster, and it struggles to explain the pattern of that ancient microwave light across the whole sky, which the dark matter picture fits with remarkable precision. The debate is not fully closed, and honest physicists on both sides admit that the other side has real points. But the weight of the evidence has moved, over decades, strongly toward the conclusion that there is a real substance out there, something that has mass and feels gravity and does almost nothing else. If it is a substance, what is it made of? The leading candidates are particles we have never detected, particles that would have to be a new kind of matter outside everything in the current catalogue of physics. One long-favoured possibility is a heavy particle that interacts only through gravity and the weak nuclear force, which would make it almost impossible to catch. For decades, physicists have built detectors to try. They place tanks of ultra-pure liquid, often xenon, deep underground, beneath mountains, shielded from the constant rain of cosmic particles, and they wait. If a dark matter particle should happen to strike the nucleus of an atom in the tank, it would produce a tiny flash of light and a whisper of charge, and the detector would record it. These experiments have grown larger and more sensitive year after year. So far, they have caught nothing. Another candidate is an extraordinarily light particle, proposed originally to solve a completely different problem in physics, which would fill space like an invisible fog. Experiments are hunting for that too. So far, silence. There is one thing dark matter does that we understand very well, even without knowing what it is, and it may be the most important thing of all. Because it does not interact with light, dark matter was free, in the early universe, to do something ordinary matter could not. In the first hundreds of thousands of years, ordinary matter was trapped in a hot, dense plasma, buffeted by radiation. Every time gravity tried to pull it into a knot, the pressure of the trapped light pushed it back apart, and it stayed smooth. Dark matter felt none of that. It ignored the light entirely. And so, while ordinary matter was still held uniform, The dark matter had already begun to collapse under its own gravity, gathering into a vast, invisible web of filaments and knots stretched across the whole young cosmos. When the universe finally cooled enough for ordinary matter to move freely, that matter fell into the gravitational wells the dark matter had already dug. Galaxies formed inside those wells. The great cosmic web that astronomers map today, galaxies strung along filaments around enormous empty voids, across billions of light years, is a map of where the dark matter went first. It built the scaffolding. Everything we can see was hung upon it. This is where the honest inventory stands. About a quarter of everything in the universe is dark matter. It outweighs all the stars and gas and dust, all the ordinary matter, by more than 5 to 1. It shaped the growth of every galaxy, including our own. Without it, the galaxies would never have held together, and the structure we see across the sky would never have formed. It is passing through you right now, in enormous numbers, a wind of unseen particles blowing through your body and through the earth as though neither were there. Because to dark matter, you are almost nothing at all. We know it is there. We can weigh it, map it, watch it steer the motion of galaxies across billions of light years. We do not know what it is. And it is not even the larger of the two mysteries. Two mysteries. That distinction belongs to something else, discovered much more recently, which is pushing the whole universe apart. We will come to it, but first we have to follow the road down into the places where gravity wins completely, into the death of stars and the objects they leave behind. A star is a balance held for a very long time. Gravity pulls every part of it inward, trying to crush the whole mass down to a point. Against that, the heat of nuclear fusion in the core pushes outward, a furnace burning hydrogen into helium, holding the star up by the pressure of its own light. For a star like the Sun, this balance lasts about 10 billion years. But it cannot last forever, because the fuel is finite, and what happens when the fuel runs out depends entirely on the mass of the star. A star like the Sun ends gently. When the hydrogen in the core is spent, the star swells into a red giant, sheds its outer layers into space in a glowing shell, and settles down into a dense, quiet ember about the size of the Earth, called a white dwarf. It no longer burns. It simply cools, slowly, over billions of years. But a star much heavier than the Sun, more than about 8 times its mass, faces something far more violent. Such a star burns through its fuel in stages, each faster than the last. It fuses hydrogen into helium, then helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. The hydrogen burning lasts millions of years, the silicon burning lasts about a day. And at iron, the furnace stops, because iron is the end of the line. Fusing iron does not release energy, it absorbs it. The moment the core turns to iron, the outward push that has held the star up for millions of years simply switches off. What follows takes less than a second. The core, more than the mass of the Sun packed into a ball a few thousand kilometers across, collapses under its own gravity, falling inward at a large fraction of the speed of light. The pressure becomes so extreme that protons and electrons are crushed together into neutrons, and a vast flood of ghostly particles called neutrinos pours out. The collapse halts only when the neutrons themselves refuse to be packed any tighter, held apart by a deep quantum rule that forbids 2 of them from occupying the same state. The infalling outer layers of the star slam into that suddenly rigid core and rebound, and a shockwave tears outward through the star and blows it apart. This is a supernova, a single dying star briefly outshining the 100 billion stars of its entire galaxy. And at the center of the wreckage, it leaves behind what the collapse created, a neutron star. Consider what that object is. Take you to its edge for a moment, though you could never truly go. You are approaching a sphere about 20 kilometers across, no wider than a city. It contains more mass than the Sun. You cannot land on it. Long before your feet reach the surface, the gravity would flatten you beyond anything the word crushing can carry. But suppose you could hold at a distance and look. The surface below you is smooth almost beyond meaning, its tallest mountains no higher than a few millimeters, held down by a gravity billions of times stronger than Earth's. It is spinning, perhaps many times every second, sweeping beams of radiation across space like a lighthouse. And a single teaspoon of the material beneath you, brought up to where you float, would weigh about as much as every human being on Earth combined. That is not a figure of speech. That is the density of matter with all the empty space squeezed out of it, the density inside the nucleus of an atom, spread across an entire star. If the collapsing core is heavier still, beyond about 2 or 3 times the mass of the Sun, even the neutrons cannot hold. There is no known force in nature that can stop the collapse. The core falls past the neutron star stage and keeps falling, the density climbing without limit, the gravity growing without limit, until the pull at the surface becomes so strong that the speed needed to escape, it exceeds the speed of light. And since nothing can move faster than light, nothing can escape. A surface forms, a boundary in space, beyond which everything is trapped. The star has become a black hole. The mathematical description of that object was found astonishingly early and under astonishing circumstances. In 1915, within weeks of Einstein publishing the field equations of general relativity, a German physicist named Karl Schwarzschild worked out an exact solution to them, describing the curved spacetime around a spherical mass. He did this while serving as an artillery officer in the German army on the Russian front, in the middle of the First World War, calculating shell trajectories by day and Einstein's equations in whatever time remained. He was already ill, suffering from a painful and incurable skin disease he had contracted at the front. He sent the solution to Einstein, who presented it on his behalf and wrote back with genuine admiration, surprised that anyone could find so clean an answer so quickly, let alone under such conditions. A few months later, in 1916, Schwarzschild died of his illness. He was 42. His solution outlived him by a century and is still the first thing every student of the subject learns. Buried in Schwarzschild's solution was something strange. At a particular distance from the center of the mass, the mathematics did something peculiar. To an observer watching from far away, time itself appeared to stop at that distance. An object falling toward it would seem to slow and freeze, hanging forever at the edge. Its light stretched and dimmed until it faded from view entirely. This distance is now called the Schwarzschild radius, and the surface it marks is the event horizon, the point of no return. For a mass equal to the Sun, that radius is about 3 kilometers. For the Earth, it is about 9 millimeters. If you could somehow crush the entire Earth down to the size of a marble, it would become a black hole. Inside the horizon, the geometry of space-time is so warped that every possible path leads inward toward the center. The singularity at the center is not a place you could steer around. It is a moment in your future as unavoidable as tomorrow. You cannot avoid falling into it any more than you can avoid moving forward in time. For a long time, almost no one believed such objects could really exist. Einstein himself did not. The mathematics allowed them, but surely most physicists felt some effect of real physics would intervene before a star could actually collapse that far. The person who first showed that the collapse could not always be stopped was a 19-year-old student crossing the sea from India to England to begin his studies. In 1930, Subramanian Chandrasekhar boarded a steamship in Madras, bound for Cambridge, and to pass the long weeks of the voyage, he worked through the physics of white dwarfs, those quiet embers left behind by ordinary stars. A white dwarf is held up not by heat but by a quantum effect, the same rule of resistance that would later stop the neutron collapse, acting here on electrons. It was thought that this pressure could hold up a white dwarf of any mass, so that every heavy star, however large, would eventually cool into one. But Chandrasekhar combined that quantum pressure with Einstein's special relativity and found something no one expected. As a white dwarf grows heavier, the electrons inside it are forced to move faster and faster, approaching the speed of light. And once they near that limit, they can push back no harder. The support gives out. There is a maximum mass a white dwarf can have, and above it, nothing can prevent collapse. He calculated that mass. It is about 1.5 times the mass of the Sun. It is now called the Chandrasekhar limit, and it means that heavy stars are doomed to become something denser than a white dwarf, neutron stars, and beyond them, black holes. Chandrasekhar arrived in Cambridge with this result and expected it to be celebrated. Instead, it was publicly destroyed. the most eminent astrophysicist in Britain, Arthur Eddington, the same man who had confirmed Einstein at the eclipse, rose at a meeting of the Royal Astronomical Society in 1935, directly after Chandrasekhar had presented his work, and tore it apart. He called the conclusion a reductio ad absurdum, and declared that there ought to be a law of nature to prevent a star from behaving in such an absurd way. He offered no real mathematical rebuttal, only the force of his authority and his certainty. Chandrasekhar, a young Indian man in a room full of senior British scientists, was given no chance to reply. The confrontation wounded him deeply. Eddington's stature was such that the field largely deferred to him, and Chandrasekhar eventually turned away from the problem and moved his research to other areas. He was proven right in the end, of course. He received the Nobel Prize for it nearly 50 years later, in 1983. He said, long afterward, that Eddington had been a great man whose very greatness had blinded him, unable to accept a beautiful result because it contradicted his sense of how nature ought to behave. The limit for a neutron star, the mass beyond which it too must collapse into a black hole, was worked out a few years after Chandrasekhar's confrontation by 3 physicists whose names are attached to it, and it lies somewhere around 2 to 3 times the mass of the Sun. The exact value still uncertain, because it depends on the behavior of matter at densities we cannot reproduce or fully understand. And in 1939, the American physicist Robert Oppenheimer, working with a student, published a paper describing the full collapse. They showed that to a distant observer, the surface of the collapsing star would appear to freeze at the horizon, hanging there forever, while to an observer falling inward with the star, nothing special would happen at the horizon at all. The fall would continue, smoothly and without pause, all the way to the singularity at the center. 2 observers, 2 completely different stories, both true. The paper was published on the 1st of September, 1939, the same day Germany invaded Poland and the Second World War began. It was almost entirely ignored. Oppenheimer turned to the atomic bomb, and the physics of black holes went quiet for another 20 years. When it woke again, in the 1960s, it woke into a different world, with better telescopes and stranger discoveries. And it was in that revival that black holes stopped being a mathematical curiosity and became one of the deepest problems in all of physics, because someone asked a simple question about them: what happens to the things that fall in? The revival of black hole physics in the 1960s was driven by the sky itself. Astronomers had begun finding objects that made no sense under the old assumptions. Quasars, points of light at enormous distances, blazing with the brightness of entire galaxies, but packed into a space no larger than a solar system, demanded an energy source far beyond ordinary nuclear fusion. The most natural explanation was matter falling into a deep gravitational well, releasing energy as it spiraled down. And in 1967, at Cambridge, a graduate student named Jocelyn Bell detected a radio signal so regular that her team, half joking and half uneasy, first labelled it with the initials for Little Green Men, before realising it was a new kind of object entirely, a rapidly spinning neutron star sweeping a beam past the Earth. If neutron stars were real, and now they plainly were, then black holes could hardly be avoided. And in the decades that followed, the last of the doubt drained away. The evidence went from suggestive to overwhelming, and finally to direct. Astronomers tracked individual stars near the centre of our own galaxy, whipping around something unseen and enormously massive, and followed their orbits for years, until the mass and smallness of the hidden object left no other explanation than a black hole, 4 million times the mass of the Sun, at the heart of the Milky Way. Then, in 2015, an experiment on the ground felt, for the first time, a ripple passing through the fabric of space-time itself, a gravitational wave set off by 2 black holes spiraling together and merging more than 1 billion light-years away. It was a faint chirp of pure geometry, lasting a fraction of a second, exactly the signal Einstein's equations had predicted a century earlier, and which Einstein himself had doubted could ever be measured. And in 2019, a network of radio telescopes scattered across the Earth, linked together to work as a single instrument the size of the whole planet, produced the first true image of a black hole, a bright ring of light bent around a dark central shadow in a galaxy some 55 million light-years away. The object Schwarzschild had described from a trench on the Russian front, that Einstein himself had refused to believe could really exist, had at last been photographed. It looked exactly as the mathematics said it should. It was around this time, in 1967, that the physicist John Wheeler used the term black hole in a public lecture, and the name stuck to the object forever. Wheeler had a gift for language, for finding the phrase that made a difficult idea suddenly graspable, and he had a habit of asking questions that seemed simple and turned out to be bottomless. The question he asked about black holes was one of those. "Imagine you take a book," he said, "and throw it into a black hole. The book is gone, swallowed past the horizon, never to return. But the information in the book, the particular arrangement of ink on its pages, the specific words in their specific order, what happens to that?" This is not an idle puzzle. It cuts to a conflict between the two deepest theories in physics. On one side, general relativity says the book falls to the singularity and is destroyed, its information erased from the universe completely. On the other side, quantum mechanics insists that information can never be truly destroyed. The evolution of a quantum system is, in principle, reversible. If you knew the exact final state of anything, you could in theory run the equations backward and reconstruct exactly what it came from. Information can be scrambled beyond any hope of practical recovery, burned, shredded, dissolved, but the underlying quantum bookkeeping is supposed to preserve it perfectly. A black hole seemed to break that rule. And when two of your most trusted theories give flatly contradictory answers to a simple question, the contradiction is not a nuisance. It is a doorway. The first step through it was taken by a young student of Wheeler's named Jacob Bekenstein in the early 1970s. Bekenstein was worrying about a different rule, the second law of thermodynamics, one of the most reliable principles in all of science. It says that the total disorder of an isolated system, a quantity called entropy, never decreases. Disorder always grows, or at best, holds steady. It is why heat flows from hot to cold and never back, why a broken cup never reassembles itself. Bekenstein imagined a simple, troubling scenario. Take a box of hot gas, which has a certain amount of entropy, a certain measure of disorder. Now drop it into a black hole. The gas is gone, past the horizon, and its entropy has vanished from the outside universe. If the black hole itself has no entropy, then the total disorder of the universe has just gone down. The second law has been broken, quietly, simply by throwing something away. Bekenstein refused to accept that. He proposed something bold. The black hole must have entropy of its own, and that entropy must increase when something falls in, by at least enough to make up for what was lost. But what would measure a black hole's entropy? A black hole, in the simplest picture, has almost no features. It is described entirely by its mass, its spin, and its charge, and nothing else. A fact Wheeler summarized by saying that a black hole has no hair. There is nothing obvious to count. Bekenstein's insight was to look at the horizon, the surface. When matter falls into a black hole, the black hole gains mass, and its horizon grows larger. Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon. Feed it, and the surface expands, and the entropy rises. The bookkeeping of the second law could be saved. The proposal had a problem, and it looked fatal. In physics, if a thing has entropy, it must also have a temperature. And if it has a temperature, then by the ironclad laws of heat, it must radiate. It must glow, however faintly, giving off energy. But a black hole, by its very definition, lets nothing escape. It is the blackest thing there is. So how could it possibly radiate? Bekenstein's idea seemed to contradict itself, and the contradiction was pointed out sharply by one of the people best equipped to judge it. Stephen Hawking, then a young researcher at Cambridge, thought Bekenstein was simply wrong, and he set out to prove it. What Hawking found instead, when he did the calculation carefully, was that Bekenstein was right, and in a way that no one had foreseen. Hawking applied the rules of quantum mechanics to the empty space just outside a black hole's horizon, something that had never been done properly before, and the empty space turned out not to be empty. According to quantum theory, the vacuum is never truly still. It seethes with pairs of particles that flicker into existence and annihilate one another almost instantly. borrowing a little energy from nothing and paying it back before the universe can notice, alone permitted by the uncertainty at the heart of quantum mechanics. Everywhere, all the time, this quiet froth of appearing and vanishing goes on, in the room around you no less than in deep space. Normally the pairs cancel perfectly and leave no trace, but at the edge of a black hole, something can go wrong with the cancellation. One member of a pair can fall across the horizon, while the other escapes outward, and once separated, they can no longer annihilate. The escaping particle carries away a sliver of energy. To someone watching from far away, the black hole appears, faintly, to glow. Hawking had proven that black holes are not perfectly black. They radiate. The radiation now carries his name. 2, and it is thermal, with a temperature that depends only on the black hole's mass. And here is the strange part. The temperature runs backward from what your intuition expects. A large, heavy black hole is extraordinarily cold, colder than the deepest cold of space. A black hole with the mass of the Sun has a temperature of less than 1/1000,000th of a degree above absolute zero. It radiates so slowly that it would take almost unimaginably longer than the present age of the universe to lose any appreciable mass. But a small black hole is hot, and as it radiates, it loses mass, and as it loses mass, it grows hotter, and so it radiates faster still. The process accelerates, running away at the very end, so that a black hole does not fade out quietly but finishes its life in a final burst, a last flash of radiation as it evaporates completely. Nothing, it turns out, lasts forever, not even the objects from which nothing can escape. Hawking's calculation did more than confirm Bekenstein's idea. It pinned down the exact relationship, fixing the precise amount of entropy a black hole carries for a given horizon area. The result is one of the most important equations in modern physics, and it now bears both their names. And when you look closely at what it says, it is deeply strange. The entropy of a black hole, which counts the number of distinct internal states it could possibly be in, all the different ways of building that particular black hole, does not grow with its volume. It grows with the area of its surface, double the radius of a black hole, and its volume grows 8-fold, as any volume does. But its entropy grows only 4-fold, in step with the area, not the volume. Sit with that for a moment, because it is the fact this whole section has been building toward, and it is not a metaphor or a loose analogy. It is a hard mathematical result, derived by combining general relativity and quantum theory, two frameworks that agree on almost nothing, in one of the rare places where they can be made to speak to each other. A black hole is an object with a 3-dimensional interior, and yet everything about it, the full count of everything it could contain, everything that ever fell in, is measured by its 2-dimensional boundary. All the information is written on the surface. The inside, in some precise and unsettling sense, holds no more than the skin. This is the seed of what would grow into the holographic principle, one of the strangest ideas in physics, and one of the most promising clues in the long search for a theory that can unite gravity and quantum mechanics. 3's under 3000. It suggests that the 3-dimensional world we live in, with all its depth and solidity, might be, in some fundamental way, a projection of information stored on a distant, lower-dimensional surface. We will return to that idea near the end of the night, because it connects, by a path no one expected, all the way back to the question of how the universe began. But the immediate consequence of Hawking's discovery was to sharpen Wheeler's old question about the book into a genuine crisis. If a black hole evaporates completely, radiating itself away to nothing over the long ages, then what happens to everything that fell in? Where does the information go? Is it carried out, somehow, in the radiation, or is it simply gone, erased from the universe, in flat violation of the laws of quantum mechanics? Hawking, at first, argued that it was gone. That answer would start an argument among physicists that lasted for the better part of 30 years. We are not ready for that argument yet. To understand what it finally revealed, we first have to go back to the beginning, to the smoothness of that ancient light we noticed at the start of the night, and to the man who, thinking about magnetic monopoles late one December evening, wrote 3 words in his notebook and changed our picture of the first fraction of a second. The hot Big Bang, for all its success, left 3 problems unsolved, and they are worth stating plainly, because the solution to all three at once is one of the most elegant moves in the history of cosmology. The first is the one we noticed at the very beginning of the night, hidden in the smoothness of the ancient light. That light has almost exactly the same temperature in every direction, to within a few parts in 100,000. And that is a problem, because regions on opposite sides of the sky have never been in contact. In the standard picture, there was simply not enough time in the whole history of the universe for light or heat or any signal to travel from one side to the other. They could not have exchanged energy. They could not have settled into a common temperature the way a hot cup and a cold room eventually meet in the middle. And yet they match precisely. It is as though you found two distant regions of the ocean, which no current had ever connected, holding exactly the same temperature to the thousandth of a degree. Something must have put them in contact, or made them from the same source, before the ordinary expansion took over. This is called the horizon problem. The second is the flatness problem. The overall geometry of space can, in principle, be curved. It could curve back on itself like the surface of a sphere, or curve outward like a saddle, or lie perfectly flat. The universe we measure is flat, or so close to flat that we cannot detect any curvature at all. And that is strange, because flatness is unstable. The equations of general relativity show that any tiny deviation from perfect flatness grows over time, rapidly. For the universe to be so close to flat now, after nearly 14 billion years of that deviation growing, it must have been almost unbelievably flat at the start. The required fine-tuning is extreme. In the first second, the density of the universe had to equal a certain critical value to something like 1 part in 1,000 trillion. A hair's breadth off in either direction, and the universe would have either collapsed back on itself long ago or thinned out so fast that no galaxy could ever have formed. Why should it have been balanced so exactly on the knife's edge? The third is the monopole problem. The best theories of particle physics predict that the extreme heat of the very early universe should have produced enormous numbers of a peculiar particle, a magnetic monopole, a particle with a single magnetic pole, a north without a south, or a south without a north. These would be heavy and stable, and they should still be everywhere today, common throughout the cosmos. We have searched, carefully, for a very long time. We have never found even one. Where did they all go? 3 problems, 3 separate puzzles about why the universe looks the way it does. In the late 1970s, a young physicist at Cornell named Alan Guth solved all 3 at once, almost by accident, while working on something else entirely. Guth was not a cosmologist, he was a particle theorist, and he had been thinking about those very monopoles and about what happens to the vacuum of space as the universe cools through certain critical temperatures. He realized that under the right conditions, the early universe could have become briefly trapped in an unusual state, a false vacuum, a configuration of empty space that carried a high, constant energy and had not yet settled down to its true, lowest energy form. And a false vacuum has a remarkable property. Its energy density does not thin out as space expands. It stays constant. And in general relativity, a constant energy density filling all of space behaves like a powerful outward pressure, driving the expansion to accelerate, not gently but ferociously, doubling and doubling the size of the universe again and again in a headlong rush. Guth worked through the numbers late one night in December of 1979, and in his notebook he wrote 2 words: spectacular realization. He had seen that a brief burst of this runaway expansion, lasting the tiniest sliver of a second in the first moments of the universe, would solve all 3 problems together. It would solve the horizon problem, because a tiny region, small enough to have reached a common temperature in the ordinary way, would be stretched by the burst to become larger than the entire observable universe. Everything we can see would have come from one small, thermalized patch, which is why it all matches. It would solve the flatness problem, because stretching any curved surface by an enormous factor makes it appear flat, the way the ground beneath your feet looks flat even though the Earth is round. And it would solve the monopole problem, because the same violent stretching would dilute the monopoles so thoroughly, spreading them across such an unthinkable volume, that there would be less than one left anywhere near us. The problem was not that the monopoles were never made, it was that the expansion scattered them almost to nothing. The scale of that expansion is difficult to hold in the mind. In a stretch of time so short it beggars description, far less than a trillionth of a second, a region smaller than a single proton was blown up larger than a grapefruit, and everything we now see, all 2 trillion galaxies, grew from that. When the burst ended, the false vacuum decayed into ordinary matter and energy, flooding the universe with hot particles, and the familiar Big Bang expansion took over from there, now smooth, now flat, now swept clean of monopoles. Guth's original version had a flaw. The way the burst ended, in his first model, would have left the universe lumpy and broken in ways we do not observe. The flaw was repaired within a couple of years, independently, by a Russian physicist named Andrei Linde, and by 2 Americans, Andreas Albrecht and Paul Steinhardt, who found ways for the expansion to end smoothly and evenly, everywhere at once. Linde went further still, showing that the burst could begin from a wide range of ordinary starting conditions, and that once it began, it might never entirely stop. In this picture, called eternal inflation, the expansion continues forever in most of space, and only ends here and there, in isolated pockets, each pocket becoming a universe of its own. Our entire visible cosmos would be one such pocket, one bubble, in an endlessly branching structure that never ceases to produce more. This is one of the roads that leads to the idea of a multiverse. It remains speculative. It follows from the equations, but the equations may not be the final word. There is one more thing inflation predicts, and it is the reason we can test it at all. The burst could not have been perfectly smooth, because nothing quantum ever is. The uncertainty at the heart of quantum mechanics guarantees a faint, restless jitter in any field, and the field that drove inflation was no exception. As the universe expanded, those tiny quantum jitters were stretched along with everything else, blown up from the microscopic to the cosmic, frozen into the fabric of the young universe as slight variations in density. Some regions a touch denser, some a touch thinner, and those slight variations were the seeds of everything. The denser regions pulled in a little more matter by gravity, and over billions of years grew into galaxies, into clusters of galaxies, into the whole web of structure across the sky. Every star, every galaxy, you, the Earth, the Sun, all of it traces back to quantum flickers in the first fraction of a second, stretched to the size of the sky. And those same variations should still be visible, imprinted on the ancient light as tiny differences in its temperature from one patch of sky to another, differences of about 1 part in 100,000. That prediction could be measured, and measuring it became one of the great experimental efforts of the age. A satellite called the Cosmic Background Explorer was launched by the American Space Agency in 1989 to study the ancient light with a precision no ground-based instrument could reach. It carried several instruments. One of them, led by a physicist named John Mather, was built to measure the exact spectrum of the light, the precise way its brightness is spread across different wavelengths. In January of 1990, at a scientific meeting, Mather presented the result, and it silenced the room before the applause began. The spectrum was a perfect match to the theoretical curve for the glow of a hot body cooled by expansion, so perfect that the error bars were smaller than the width of the line drawn on the graph. The data points sat exactly on the prediction. It was, and remains, one of the most precise agreements between theory and measurement ever achieved in physics. The hot Big Bang was confirmed at a level no rival theory could touch. A second instrument on the same satellite, led by a physicist named George Smoot, had the harder task. It was built to map the tiny differences in temperature across the sky, the faint imprint of those primordial seeds. The signal was minute, buried under noise, under the glow of our own galaxy, under the effects of the Earth's own motion, and it took years of painstaking analysis to draw it out. In April of 1992, the team announced they had found it. Patches of sky slightly warmer and slightly cooler than the average, at the level of a few parts in 100,000, exactly as inflation had predicted, the oldest structures ever seen, the seeds of every galaxy that would ever exist. At the announcement, Smoot reached for a description of what the map showed and said that if you were religious, it was like looking at the face of God. The remark irritated some of his colleagues, but it caught the scale of the thing. What that map showed was the universe at an age of 380,000 years, a vast sphere of glowing plasma just becoming transparent, faintly rippled with the patterns from which everything would grow. Later missions sharpened the picture enormously. A probe named for the physicist David Wilkinson mapped those temperature ripples with many times the detail of the first satellite. Then a spacecraft called Planck, launched by the European Space Agency, sharpened them further still and measured not only the temperature of the ancient light but the subtle way it is polarized. From the fine pattern of those ripples, cosmologists have read off the age of the universe, its composition, its geometry, and the detailed statistics of the primordial seeds, and they match the simplest predictions of inflation to remarkable precision. There is one prediction, still being hunted, a faint twisting pattern in the polarization of the light that would be the fingerprint of gravitational waves generated by inflation itself, ripples in spacetime, from the first instant. A detection would be a direct glimpse of physics at energies we can never hope to reach in any machine on Earth. Once, a team operating a telescope at the South Pole announced they had found it, and for a few weeks it was the most exciting result in cosmology, until closer analysis showed the signal was contaminated by dust in our own galaxy. The search goes on. The telescopes are still watching, at the South Pole and in the high desert, and the limits tighten, year by year. Inflation explains the smoothness, the flatness, the missing monopoles, and the origin of all cosmic structure. It is a triumph. And it does not answer the deepest question at all. It tells us what happened in the first fraction of a second, but not what came before that fraction, nor what set the burst in motion, nor what the field that drove it truly was. And there is a further mystery it leaves entirely untouched. The expansion inflation started did not stop. It slowed, for billions of years, as gravity pulled back against it. And then, a few billion years ago, it began to speed up again, driven by something we understand even less than we understand the beginning. All through the 1990s, astronomers expected the expansion of the universe to be slowing down. It seemed obvious. Gravity pulls. Every galaxy tugs on every other across the emptiness, and that mutual pull should act as a brake on the expansion, gradually reining it in. The only question worth asking, they thought, was how hard the brake was pressing. And the answer to that question would decide the fate of everything. If there was enough matter in the universe, its gravity would eventually halt the expansion and reverse it, drawing all the galaxies back together into a final collapse, a mirror image of the Big Bang, sometimes called the Big Crunch. If there was too little matter, the expansion would coast onward forever, thinning and cooling into endless dark. The whole future of the cosmos came down to measuring how quickly the brake was slowing things down. To measure that, you had to look deep into the past, because looking far into space is looking back in time. Light from a galaxy 1 billion light-years away has been traveling for 1 billion years, and shows you that galaxy as it was when the light set out. If you could measure how fast very distant galaxies were receding, and compare it to how fast nearby ones recede, you could reconstruct the whole history of the expansion and see how much it had slowed. But for that you needed a reliable way to measure the distances to objects billions of light-years away, and that meant you needed a standard candle, a kind of object whose true brightness you already knew, so that its apparent faintness would tell you exactly how far off it was. Nature provides one, and it is spectacular. It is a particular kind of stellar explosion called a Type 1, a supernova. It happens in a binary system, where a white dwarf, that quiet ember left by an ordinary star, is paired with a companion, and pulls matter from it, slowly gaining mass. Recall the Chandrasekhar limit, the maximum mass a white dwarf can hold before its support gives out. As the white dwarf feeds and approaches that limit, it reaches a point of no return, and a runaway wave of nuclear fusion ignites and tears the entire star apart in a single titanic blast. Because the trigger is always the same, always that same critical mass, these explosions all reach very nearly the same true brightness. There are small variations, but they track the way the light fades afterward. So the light curve itself reveals the intrinsic brightness. Measure how bright the explosion appears from Earth. Compare it to how bright it truly is, and you have the distance. And a Type 1, a supernova, for a few weeks, can outshine a galaxy, which means it can be seen almost all the way across the visible universe. It is a standard candle you can light billions of light-years away. Two teams set out, in fierce competition, to use these explosions to measure the slowing of the universe. One, based in California and led by Saul Perlmutter, had been at it since the late 1980s. The other, led by Brian Schmidt in Australia and Adam Rees in the United States, started a few years later. Both faced the same brutal difficulty. These supernovae are rare, and they appear without warning, a single point of light flaring in a distant galaxy among countless others. The teams developed a way to catch them, photographing wide fields of the sky, then photographing the same fields again weeks later and subtracting one image from the other, so that everything unchanging cancelled out and only the new points of light remained. Then they had to race to capture each one with the largest telescopes, on the ground and in space, measuring its light and its distance before it faded. It was exhausting, technical, uncertain work, stretched over years. And when the results finally came in, at the end of the 1990s, they made no sense. The distant supernovae were too faint, not by a little, by enough to be alarming. In the framework everyone was using, too faint meant too far away, farther than they should have been if the expansion had been slowing all this time. The universe was not decelerating, it was accelerating. Something was pushing the galaxies apart, overcoming the pull of all that matter, and had been doing so for billions of years. Both teams were deeply unsettled. Rees, working through his team's data, spent weeks hunting for the error he was sure must be there. Perhaps dust was dimming the supernovae. Perhaps the ancient explosions were somehow different from the nearby ones. Perhaps the calibration was off. He checked each possibility, and each one failed to explain the result away. The data would not budge. Perlmutter's team, arriving at the same answer by a separate road, went through the same crisis of doubt. In early 1998, both teams published, within weeks of each other, and their conclusions agreed. The expansion of the universe is speeding up. 13 years later, the three men who led the work shared the Nobel Prize. The acceleration meant that space is filled with some form of energy, unlike matter, unlike radiation, that does not pull inward but pushes outward, because it does not clump, does not glow, does not absorb or emit any light, and reveals itself only through its effect on the expansion of the universe as a whole. It was given a deliberately vague name, dark energy, and the simplest thing it could be is an old ghost returning. It could be Einstein's cosmological constant, the very term he had inserted into his equations to hold the universe still, and then abandoned in embarrassment when Hubble showed the universe was moving. The blunder had come back, transformed, not as a force to prevent expansion, but as the explanation for why the expansion is now growing faster. In this reading, the cosmological constant is the energy of empty space itself, a constant density of energy inherent to the vacuum, present in every cubic meter of nothing. As the universe grows, matter thins out, its density dropping as the same amount of matter spreads through more space. But the energy of the vacuum does not thin. Every new cubic meter of space comes with its own share. And so, as the universe expands and matter fades, the vacuum energy comes to dominate, and its outward push wins, and the expansion accelerates. Here is where the mystery deepens into something close to embarrassment for physics. The measured value of this vacuum energy is astonishingly, almost absurdly, small. It amounts to roughly the energy of a few protons in every cubic meter of space, so faint that it went completely unnoticed until the universe had grown old enough and large enough for its cumulative effect to overtake gravity. And yet, when physicists try to calculate what the energy of the vacuum ought to be, using quantum theory, adding up the restless froth of all those flickering particle pairs in empty space, they get a number that is larger than the measured value by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is the single worst prediction in the history of science, the largest gap ever recorded between what a theory says and what the world shows. Some deep cancellation must be at work, reducing the enormous theoretical vacuum energy almost, but not quite, to zero. Why it should be cancelled so precisely, and yet left with exactly the tiny remainder that we observe, a remainder that happens to be just small enough to allow galaxies to form and life to arise, is one of the deepest unsolved problems in all of physics. No one knows the answer. The acceleration also settles the fate of the universe, at least if dark energy is truly a constant. If it is, the expansion will continue to accelerate forever. The consequences are quietly stark. Over the coming tens of billions of years, the accelerating expansion will carry distant galaxies away from us faster and faster, until their light is stretched beyond detection and they slip, one by one, past the edge of what we can ever see. Far in the future, an astronomer in our galaxy, or what our galaxy has merged into, will look out and find the sky empty of everything but the nearest few galaxies, gravitationally bound to us and safe from the expansion. The rest will be gone, beyond any possible observation, their existence unguessable. The universe will appear, to those future observers, small and lonely, the grand evidence of the Big Bang itself faded past recovery. And beyond that, over spans of time that dwarf the current age of the universe many times over, the stars themselves will burn out, one generation after another, until star formation ends and the last stars cool, and the cosmos settles toward a thin, cold, uniform darkness. There are other possibilities. If dark energy is not a true constant but something that changes with time, it might weaken, letting gravity reassert itself. It might strengthen, tearing the universe apart in a final catastrophe that shreds galaxies, then stars, then planets, then atoms. The current measurements are consistent with a simple constant and with the long, cold fade, but the uncertainty leaves the door open. When we add it all up, the accounting is humbling. The universe, as best we can measure it, is about 68% dark energy, about 27% dark matter, and just under 5% ordinary matter. Everything you have ever seen, every star and planet and galaxy, every atom of every living thing, every page of every book ever written, the entire visible cosmos, is that last 5%. The other 95% is dark, invisible, and barely understood. One dark component holds the galaxies together, the other is pushing the universe apart. We can measure both with real precision. We can map where they are and how they behave and how much of each exists. We cannot say what either of them is. This is the honest state of cosmology. We have built a picture of the universe that fits the data beautifully, and the picture is mostly made of things we cannot name. There is even a crack showing in the measurements themselves, and it has stubbornly refused to close. There are two main ways to measure how fast the universe is expanding today. One works outward from the early universe, reading the expansion rate off the fine pattern in the ancient light. The other works inward from nearby galaxies, using pulsing stars like the ones Leavitt studied, and exploding stars as a ladder of stepping stones to gauge distances directly. For a long time, the two methods were too rough to compare. As they sharpened, everyone expected them to converge on a single number. Instead, they have drifted apart and stayed apart, disagreeing by several percent, each with error bars now too small to explain the gap away as mere sloppiness. Something does not fit. It may be a subtle error still hiding in one of the methods. Or it may be a real sign that the simple picture is incomplete, that there is new physics in the dark sector we have not yet grasped. No one knows which. It is one more open door, standing ajar at the frontier. And yet, for all that we do not know, everything in this picture flows from the equations Einstein wrote in 1915. General relativity, with a cosmological constant added back in, describes the large-scale universe with extraordinary precision, from the orbit of Mercury to the bending of starlight to the expansion of the whole cosmos to the ripples in the ancient light. The theory works magnificently across an enormous range of scales. The mysteries lie at the edges, where the theory reaches conditions so extreme it begins to break down. At the center of every black hole, where the density climbs without limit, and at the very beginning, where the expanding universe, traced all the way back, converges toward a single point, and the theory predicts its own failure. That point, the singularity at the start of time, is where we turn next. And it is there, at the place where our best theory confesses that it cannot go, that the strangest idea of the night is waiting. The question of what came before the beginning is older than science. It is older than telescopes, older than physics, as old as the first person who lay awake wondering how everything got started and what, if anything, came first. And for most of history it seemed to lead into a trap, If the universe began at some moment, then what was there before? And if you say nothing, the mind rebels. Because why then would nothing suddenly become something at that particular moment and not another? And if you say the universe always existed, stretching infinitely into the past, the mind rebels at that too, because an infinite past is its own kind of impossibility, an endless corridor with no first step. Isaac Newton had given the question its modern shape. He imagined time as an infinite straight line, running backward and forward without end, existing on its own, indifferent to anything in it. On that line, the universe was created at some point, wound up like a clock and set running. But this only sharpens the trap. If time itself is infinite and empty, and the universe appears at one instant on it, the question of why that instant becomes unanswerable, and so does the question of what filled the endless time before. The German philosopher Immanuel Kant, in the 1780s, laid the trap out with painful clarity. He showed that you could construct a convincing argument that the universe must have had a beginning in time, and an equally convincing argument that it could not have, that it must stretch back forever. Two airtight proofs, reaching opposite conclusions. He called such a pair an antinomy, and he took it as a sign that human reason had wandered past the edge of what it could handle. Time and space, he concluded, are not features of the world as it is in itself. They are the framework our own minds impose in order to experience anything at all. The question of the beginning is unanswerable, he thought, because it asks about something beyond the reach of any possible experience. Kant's escape was philosophical. Einstein's was physical, and far more radical. General relativity does not treat time as an infinite line laid down in advance. It makes time part of the universe, woven into the same fabric as space, shaped and stretched by the matter and energy the universe contains. There is no cosmic clock ticking in the background, independent of everything. Time is internal. It began when the universe began, and this reframes the old question completely. Asking what came before the Big Bang, in this picture, becomes like asking what lies north of the North Pole. There is no such place, not because it is hidden or too far away, but because north runs out at the pole. The question dissolves. Time is a property of the universe, and at the beginning, that property simply does not extend any further back. This is a satisfying answer, but it rests on the singularity, and the singularity is exactly where the theory breaks down. If the beginning is a point where general relativity gives infinite, meaningless answers, then the confident claim that time began there is standing on very thin ice. Perhaps a deeper theory, one that does not break down, would replace the singularity with something else, something that changes the whole story. And to know whether the singularity is truly a beginning, or merely a place where our current theory fails, physicists first had to establish whether it was even real, or just an artifact of the simplified models used to describe it. That question was settled in the mid-1960s by Roger Penrose and Stephen Hawking. Using a new and powerful way of tracing the paths that light can take through curved spacetime, Penrose proved that when a massive star collapses, the formation of a singularity at its center is not a special case that depends on perfect symmetry. It is unavoidable, a general consequence of the theory, forced by the geometry itself once the collapse passes a certain point. Hawking then took the same mathematical machinery and turned it around, running it not forward into a collapsing star but backward into the expanding universe. If the universe is expanding, and if general relativity holds, and if the matter in it behaves in ordinary ways, then the paths traced backward in time must converge. There must be a singularity in the past. Time must have a beginning. The singularity theorems, as they came to be called, showed that the beginning was not an accident of a simplified picture. It was built into the structure of Einstein's theory, but even the theorems carry the seed of their own limit, and Hawking knew it. They assume that general relativity holds all the way down to arbitrarily small sizes and arbitrarily high densities, and there is every reason to believe it does not. At extremely small scales, around a size called the Planck length, so small that a proton is to it roughly as a galaxy is to a person, the smooth geometry of general relativity should dissolve into the restless uncertainty of the quantum world. General relativity is a classical theory. It knows nothing of the quantum jitter, the fundamental fuzziness that governs everything small, At the singularity, that ignorance becomes fatal. To describe the true beginning, you would need a theory that fuses general relativity with quantum mechanics, a theory of quantum gravity, and that theory does not yet exist, not in complete form. What exists are partial approaches, sketches, glimpses, and one of the most beautiful of them was proposed by Hawking himself, together with James Hartle, in 1983, building on an idea from the physicist Richard Feynman. To understand it, you have to understand Feynman's strange and wonderful reformulation of quantum mechanics, which he developed in the 1940s. In everyday physics, an object goes from one place to another along a single, definite path. You throw a ball, and it traces one arc through the air. Feynman proposed that a quantum particle, going from one point to another, does not take a single path. It takes every possible path at once, all of them simultaneously, the direct route and the wild detours and the loops out to the edge of the galaxy and back. Each path is assigned a number, and when you add up the numbers for all the infinite paths, most of them cancel each other out, interfering and destroying one another, and what survives, the path that adds up constructively, is the one classical physics would have predicted all along. The particle does not choose. It explores everything, and what we observe is the sum of all of it. This sum over histories approach gives exactly the same predictions as ordinary quantum mechanics, but it suggests a completely different way of thinking. Reality, at bottom, is not a single history. It is a sum over all possible histories. Hartle and Hawking asked what would happen if you applied that idea not to a single particle, but to the entire universe. Instead of a particle taking every path, the universe would take every possible history, every possible shape of spacetime, universe, every possible arrangement of geometry and matter, all summed together to give the quantum state of the cosmos as a whole. And this raised a sharp question. In the ordinary way of doing physics, to work out how a system evolves, you must specify its starting conditions, its state at some initial moment, its boundary in time. But what could it possibly mean to specify the starting conditions of the universe, the boundary at the very first instant, when there is nothing before it to set those conditions? Hartle and Hawking's answer was as elegant as it was strange. There is no such boundary. The universe has no initial condition to specify, because it has no edge in time at all, and the way they made that mathematically precise was through the idea of imaginary time. Imaginary time sounds like something from fiction, but it is a concrete and well-defined mathematical object. Ordinary numbers, the ones we count and measure with, physicists call real. There is another kind, called imaginary, built from the square root of -1, a quantity no ordinary number can produce. Imaginary numbers began as a curiosity, and turned out to be woven all through physics, indispensable wherever waves and oscillations appear. In the equations of relativity, there is a crucial difference between the time direction and the three directions of space, marked by a single stubborn minus sign that sets time apart from the rest. But if you perform a particular mathematical operation, replacing ordinary time with imaginary time, that minus sign vanishes. And when it vanishes, the difference between time and space vanishes with it. Time becomes just another direction, indistinguishable from the three spatial ones. The 4 dimensions of space-time become 4 dimensions of a smooth, seamless space, with no direction singled out as special, no arrow, no flow, no before and after. In that framework, the history of the universe can be modelled as a closed, 4-dimensional surface, finite in size but with no boundary and no edge, like the surface of a sphere given more dimensions. And now the old image from the very start of the night returns, and does its real work. Think of the surface of the Earth. It is finite. It has a definite area. You could walk across all of it, given time, and come back to where you began. And yet it has no edge, no boundary, no place where the ground stops and the void begins. At the South Pole, the concept of south simply runs out. There is nothing south of it, not because a wall blocks the way, but because south has no meaning there. Every direction from the pole is north. The Big Bang, in the no-boundary picture, is exactly like the South Pole. It is not a jagged edge where the universe began from nothing. It is a smooth, ordinary point on a closed surface, where the direction we call the past simply runs out. And never, The question of what came before is not a hard question that science has failed to answer. It is a question that misunderstands the shape of the thing, in the same way that asking what lies south of the South Pole misunderstands the shape of the Earth. There is no before, because there is no boundary in time for a before to occupy. The universe is finite in the past, and yet it has no beginning. It is self-contained. It requires nothing outside itself. The no-boundary proposal does not do away with the need for a full theory of quantum gravity. It is an approximation, a way of stitching general relativity and quantum mechanics together in one particular regime, and it may or may not survive when the complete theory is finally found. But it is not empty speculation, it makes predictions. It predicts that the universe should have emerged smooth and regular, with just the faint quantum ripples needed to seed galaxies, and the spectrum of those ripples can be calculated and compared to the ancient light, and it roughly matches. It tends to favour a universe that is spatially closed, curved gently back on itself, finite in extent, though large enough to appear flat to us, the way a small patch of an enormous sphere looks flat to someone standing on it. The measurements do not yet decide the matter one way or the other. The proposal remains a proposal, subject to test, possibly never provable in a final and definitive sense. But its deepest implication is not any single number or prediction. It is a shift in how the origin question can be framed. For centuries, the universe was imagined as a made thing, a mechanism assembled and set going by something outside it. The old argument that the complexity of the world implies a maker rested on the assumption that the universe had a beginning, and that a beginning demands a cause. The no-boundary proposal quietly removes the need for a cause, not by disproving one, but by dissolving the question that a cause was meant to answer. A universe with no boundary in time is not an event that happened. It is not a thing that began. It is the whole of time, a complete and closed structure, and asking what caused it is like asking what is north of the North Pole. This is not a proof about God in either direction. It settles no ancient argument about ultimate purpose. It is a piece of theoretical physics, grounded in mathematics, open to test, and it stands as a genuine alternative to the picture of a universe with a sharp first edge. And it arrives by a long and unbroken chain of reasoning from the same equations that bend starlight around the sun and slow the clocks on moving trains. That leaves one last thread to gather, the strangest of them all. The one we left hanging when a black hole taught us that the information of a whole volume can be written on its surface. Because that fact, it turns out, may reach all the way back to the beginning, and change what the beginning even is. Return, then, to the book thrown into the black hole, and to the crisis Hawking's discovery had created. Once it was clear that a black hole slowly radiates itself away, evaporating over the long ages until nothing is left, the question of what happens to the information inside became impossible to avoid. Everything that ever fell in, every book, every star, every detail of everything the black hole had swallowed, seemed to face two fates that could not both be true. Either the information was destroyed when the black hole vanished, which would break the deepest rule of quantum mechanics. That information is never lost. Or the information somehow escaped, carried out in the radiation, which seemed impossible, because the radiation appeared to be featureless heat, the same regardless of what had gone in. Hawking took the first side. He argued, from the mid-1970s onward, that the information was simply gone, destroyed, and that quantum mechanics would have to be modified to allow it. This was a startling position, because it meant sacrificing one of the most trusted principles in physics to save another. Not everyone accepted it. On the other side stood Leonard Susskind, a physicist at Stanford, and Gerard Hooft, a Dutch physicist who had won the Nobel Prize for foundational work in quantum theory. To them, the destruction of information was unthinkable. If it could happen inside a black hole, the reliability of quantum mechanics everywhere came into question. They were certain the information had to survive, somehow, and they set out to find out how. The disagreement that followed lasted, on and off, for nearly 30 years. Susskind later called it the Black Hole War, though it was fought not with weapons but with seminars and papers and a slow, grinding accumulation of insight, and it led, in the end, to one of the strangest and most productive ideas in modern physics. The turning point grew out of that fact from before, the one that should still be sitting uneasily in your mind. The entropy of a black hole, the full count of everything it could contain, is proportional to the area of its horizon, not to its volume. All the information lives on the surface. Susskind and Hooft took that seriously, more seriously than anyone had, and asked what it would mean if it were not a peculiarity of black holes but a general truth about the universe. The result was the holographic principle. It says that everything happening inside any region of space can be completely described by information stored on the boundary of that region. The three-dimensional world, with all its depth and solidity, would be, in some precise sense, a projection of information encoded on a distant two-dimensional surface. The way a flat holographic plate can store the image of a solid object and throw it, seemingly three-dimensional, into the air. The maximum amount of information that can be packed into any region of space is set not by its volume, as every intuition insists, but by its surface area. This is not offered as a metaphor, it is offered as a law of nature. For years it remained a bold conjecture, compelling but unproven, until in 1997, a young physicist named Juan Maldacena found a concrete case where it was demonstrably mathematically true. Maldacena was working within string theory, and he considered a particular kind of universe, a curved spacetime called anti-de Sitter space, shaped something like a saddle, with a peculiar geometry that does not match our own universe, but is mathematically clean to work with. He showed that a full theory of gravity operating inside that five-dimensional space was exactly equivalent to a different theory, one containing no gravity at all, living on the four-dimensional boundary of that space. The two descriptions, one with gravity in a higher dimensional interior, one without gravity on the lower dimensional surface, were not merely similar, they were the same physics, written two ways. Every object, every event, every calculation in the interior had a precise counterpart on the boundary. Anything you could compute one way, you could compute the other way, and get the identical answer. It became one of the most cited results in the history of physics. Maldacena's correspondence did not describe our universe. Our universe is expanding, with a positive vacuum energy, not the saddle-shaped space he used. But that was almost beside the point. What he had shown was a proof of principle, an existence proof, a case where a world with gravity was demonstrably identical to a world without gravity in one fewer dimension. The holographic idea was no longer just philosophy. It was concrete mathematics in at least one setting. And if it holds in one setting, there is good reason to suspect it reflects something general about the way gravity and quantum mechanics fit together, which means it might hold, in some form, for the universe we actually inhabit. The three-dimensional space you are lying in, the room, the Earth, the galaxies, might all be encoded on a surface somewhere, projected into the depth we experience by a mechanism we do not yet understand. The consequences of this idea run very deep, deeper than any single experiment. For decades, the great obstacle to uniting gravity and quantum mechanics has been that the two speak incompatible languages. General relativity is a theory of smooth, continuous geometry, of space-time bending gracefully. Quantum mechanics is a theory of discrete jumps and probabilities and fundamental fuzziness. They clash precisely where both matter at once, at the singularity, at the black hole horizon, at the beginning of time. The holographic principle hints at a way through, and it is a strange way. Perhaps the problem is that we have been treating space-time as fundamental, as the bedrock on which everything else rests. Perhaps it is not. Perhaps space itself, and the third dimension of depth in particular, is not a basic feature of reality, but something that emerges from a deeper layer, a layer made not of points in space, but of pure information organized on a boundary. In that view, the smooth space-time of general relativity is a kind of large-scale illusion, a convenient description of something more basic underneath, the way the smooth surface of water is a convenient description of countless separate molecules. If space is emergent, then the search for quantum gravity has been aiming at the wrong target. You do not quantize space-time, you watch it emerge. None of this is settled. The holographic principle is proven only in special cases, and how it applies to a universe like ours remains genuinely unclear. But it has reshaped the questions physicists ask, and it grew, by an unbroken thread, out of a young student's worry about a box of gas and the second law of thermodynamics. out of Hawking's calculation of a faint glow at the edge of a black hole, out of Schwarzschild's wartime solution, all the way back to Einstein's falling man. And it connects forward, too, to the beginning of the universe. Because if the information of a whole region can be written on its boundary, then the singularity at the start of time may not be a place where physics fails at all. It may be a place where our three-dimensional intuition about what a beginning must be simply does not apply, in the same way that the intuition of depth does not apply to a hologram. The clue is written in the area of a horizon, in an equation that ties the death of a star to the birth of everything. And to see how that clue was chased further into the deepest current theories of matter and space, we have to look at the framework Maldacena was working inside, the one that has spent half a century trying to become a theory of everything. String theory began, in the late 1960s, as an attempt to describe the strong nuclear force, the force that binds the cores of atoms together. It did not succeed at that task, and was set aside for it, replaced by a better theory. But before it was abandoned, physicists noticed something odd buried in its mathematics. The theory kept producing a particle it had not been designed to produce, a massless particle with a particular kind of spin, and there was already a place in physics waiting for exactly such a particle. According to general relativity, the gravitational force should be carried by a massless particle with precisely that spin, a particle called the graviton. String theory, built to describe a completely different force, had accidentally produced gravity. It could not get rid of it. That was the first hint that this failed theory of the nuclear force might be something much larger, a candidate for a theory that could describe everything, gravity included, in a single mathematical language. That hope has driven the field ever since. The core idea is a change in what the fundamental things are. In ordinary physics, the basic constituents of matter are point particles, objects with no size, located at single points. String theory proposes instead that the basic constituents are tiny, vibrating strings, one-dimensional loops and threads, unimaginably small, and every kind of particle corresponds to a different way the string can vibrate, a different note. An electron is a string vibrating one way. A photon is the same kind of string vibrating another way. The graviton is another note again. All the bewildering variety of particles, all the different kinds of matter and force, would be, in this picture, different harmonics of a single kind of object, like the different notes a single string on an instrument can play. It is a genuinely beautiful idea. Its difficulty is that the strings are thought to be about as small compared to a proton as a proton is compared to a solar system, far too small for any conceivable experiment to see directly. The theory is guided almost entirely by mathematical consistency, rather than by measurement, which is both its strength and the source of the deepest doubts about it. One of its stranger requirements is extra dimensions. The mathematics of string theory refuses to work in the 3 dimensions of space and one of time that we experience. It demands more, 6 additional spatial dimensions beyond the familiar 3, making 9 dimensions of space in all, plus time. Where are they? The standard answer is that they are curled up, wound so tightly and on such a small scale that we never notice them. The way a garden hose seen from far away looks like a one-dimensional line, though up close its surface is a 2-dimensional sheet wrapped into a tube. The 6 extra dimensions are imagined as folded into intricate tiny shapes, and the particular shape they take, its precise geometry, would determine the properties of all the particles and forces we observe in the large dimensions we can see. But there is no unique shape. The mathematics permits an enormous number of possible ways to fold the extra dimensions, each producing a different set of physical laws. This vast catalogue of possibilities, sometimes called the landscape, has been a source of deep frustration, because a theory that allows almost any outcome struggles to predict our particular one. For a while there was another embarrassment. There was not one string theory but 5 different mathematically consistent versions, and no one knew which, if any, described reality. Then, in the mid-1990s, a series of discoveries revealed that the 5 were not really separate theories at all. They were 5 different views of a single deeper thing, connected by hidden mathematical equivalences, so that a strongly interacting version of one was identical to a weakly interacting version of another, a large space in one identical to a small space in another. The physicist Edward Witten drew these threads together and named the underlying structure M-theory. He has never officially said what the M stands for, suggesting playfully that it might be for magic, or mystery, or membrane, and that each person could choose. M theory lives in 11 dimensions, and its fundamental objects are not only strings but membranes of various dimensions, which physicists call branes. A brane is an extended surface, and it can have any number of dimensions. A brane with 1 dimension is a string. A brane with 2 is a sheet. A brane with 3 fills all the space we move through, and to anything living on it, it would appear to be an entire 3-dimensional universe. And this suggests a genuinely startling possibility. Our whole universe might be a 3-dimensional brane, floating in a higher dimensional space, like a single sheet of paper suspended in a much larger room. All the particles and forces we know, all of matter, all of light, might be confined to the surface of that brane, stuck to it, unable to leave, all except one. Gravity, being the bending of space-time itself rather than a thing that lives within it, might not be confined. Gravity might leak off the brane, spreading out into the full higher dimensional space around it. And this could explain a long-standing puzzle, which is why gravity is so absurdly weak compared to the other forces. A small magnet can pick up a paperclip against the pull of the entire Earth. Gravity may not be truly weak at all. It may only seem weak to us because most of its strength is draining away into dimensions we cannot perceive. In 1999, the physicists Lisa Randall and Raman Sundram worked out detailed models along these lines, in which an extra dimension is warped, its geometry curved in a way that changes the apparent strength of gravity, and showed that such an extra dimension could even be infinitely large and still remain hidden from us. Their work also offered a new and speculative way of thinking about dark matter, the invisible substance we met earlier in the night. Perhaps, in some versions, there is another brane, a shadow world, running parallel to ours and separated from it only by a short distance in the extra dimension. Matter on that shadow brane would pull on our matter through gravity, which leaks across the gap, but would be invisible to us in every other way, sending us no light, no signal, nothing but a gravitational tug. The dark matter holding our galaxies together might be ordinary matter, on a neighbouring world, close by in a direction we cannot point to and can never reach. It is speculation, but it is speculation grounded in the same mathematics that produced Maldaceno's correspondence, not a guess pulled from the air. Can any of this be tested? That is the hard question that hangs over the whole enterprise. If the extra dimensions are curled up at the smallest imaginable scale, no experiment will ever reach them directly. But if they are somewhat larger, or warped in the right way, there might be signs. Physicists have searched for them at the largest particle accelerator ever built, the Large Hadron Collider, looking for collisions in which a little energy goes missing, carried off by a particle escaping into the extra dimensions. They have found nothing. They have searched for tiny deviations in the strength of gravity at very short distances, which extra dimensions might produce. Nothing so far. Every measurement remains consistent with a universe of exactly 3 spatial dimensions and no more. The theoretical case for string theory rests on its mathematical beauty and its unique ability to contain gravity. And its critics point out, not unfairly, that a theory which has made no confirmed prediction in half a century is on uncertain ground. Its defenders reply that the problems it addresses are the hardest in all of physics, and that beauty and consistency have guided the field correctly before. The argument is unresolved, and honest people stand on both sides. Whatever the final verdict on string theory, the brain picture offers one more perspective on the question that has run through the whole night, the question of the beginning. If our universe is a brane in a higher dimensional space, then the Big Bang, the south pole of our 4-dimensional history, might be a smooth and ordinary feature of a larger, higher dimensional geometry that has no boundary of its own. The question of what came before would dissolve in the same way once again. There would be no before, only a larger structure that contains our beginning as a surface within it. The holographic principle, the brane worlds, the no-boundary proposal, these are not competing answers, fighting for the same ground. They are threads of one attempt, approached from different directions, to describe a universe that somehow contains both the smooth curve of gravity and the restless jitter of the quantum, both the vast and the tiny, in a single consistent picture. None of them is finished. All of them are the frontier, the place where our understanding runs out and the next understanding has not yet been found. There is one more thread, and it is uncomfortable, and it must be named honestly. In the landscape of string theory, with its uncountable possible universes, and in the eternal inflation that endlessly buds off new bubbles, there arises the idea that our universe may be one of a great many, most of them utterly different, most of them incapable of holding together long enough or gently enough for anything interesting to happen. And this offers a particular kind of answer to why our universe seems so finely suited to us, why the vacuum energy is small enough for galaxies to form, why the forces have the strengths they do, why matter is stable. The answer, in this view, is a selection effect. In the vast majority of universes, no observer could ever exist to ask the question. We necessarily find ourselves in one of the rare ones where the conditions allow stars and planets and living things, because those are the only universes where anyone is present to look around and wonder. This is called the anthropic principle, and it is not an explanation in the ordinary sense. It is a constraint, and to many physicists, it is a deeply unsatisfying one, an admission of defeat dressed as an answer. To others, it is simply the honest consequence of a cosmos far larger and stranger than the one we can see. Which it is, no one yet knows. It sits at the very edge of what physics can currently say, one more open question in a night that has been full of them. And these questions, all of them, are the direct descendants of the ones a young man asked at a wooden desk in Bern more than a century ago. What is time? What is space? What is the relationship between the one who observes and the thing observed? The answers have grown stranger with every generation, reaching from a slowed clock on a moving train all the way to the possibility that space itself is a projection and the beginning of everything has no edge. But the questions have not changed. They are the same questions. We are simply asking them from much further out. Now, at the end of the night, return to the image that opened it. A globe. Hold it in your mind again, as you held it hours ago, when the words were only beginning. Trace the lines of longitude down from the equator. They converge. At the South Pole, all directions become north. There is no south of the South Pole. The surface of the globe is finite. It has an area you could measure, a distance you could walk, and if you walked it, you would come back to where you started. And yet it has no edge. There is no boundary, no wall, no place where the Earth stops and something else begins. The question, what lies beyond the South Pole, does not fail because it is difficult. It fails because it misunderstands the shape of the thing it asks about. The no-boundary proposal says the universe is like that globe, not in space, but in time. Its history is a closed, smooth surface, complete in itself, with no sharp first edge and no need for a cause standing outside it. The Big Bang is not a moment when the universe leapt into being out of nothing. It is an ordinary point, like the South Pole, where the geometry is gentle and well-behaved, and where the direction we call the past simply runs out. The question, what happened before the Big Bang, is not a question that science has failed to answer. It is a question that, in this picture, does not apply. Time is a property of the universe, not a stage the universe was placed upon. The cosmos does not require a first cause, because it has no boundary in time for a cause to act across. It is finite in the past, and it has no beginning. This is where a century of thought has arrived, following a single thread. It began with a young man wondering what it would be like to ride alongside a beam of light, and that question broke the absolute clock. The next question, what gravity really is, bent spacetime into a shape and set the whole cosmos in motion. The flight of the galaxies traced that motion back to a dense and blazing origin. The study of collapsing stars showed that singularities are real and that the full contents of a volume can be written on its surface. The invisible mass in the galaxies and the accelerating expansion of space revealed that almost everything is made of things we cannot name. And the no-boundary proposal, weaving the quantum into the fabric of spacetime, suggested that the beginning might not be a beginning at all. None of it is finished. That is the honest ending, the only one this material allows. We do not know what dark matter is, though we can weigh it and watch it steer the galaxies. We do not know what dark energy is, though it is deciding the fate of everything. We do not know what happens to the information that falls into a black hole, though 30 years of argument have taught us the answer lies somewhere in the strange fact that a volume can be described by its surface. We do not know whether space itself is fundamental or a projection from somewhere deeper. We do not know whether the universe is one or one of an endless many. And we do not know whether the no-boundary proposal is true, only that it is possible, and that it follows, step by careful step, from the same equations that bend starlight around the sun and slow the clocks on a passing train. It has not been proven, it may never be proven in a final sense, but it is there, a genuine answer to one of the oldest questions human beings have ever asked, and it is not made of mysticism, it is made of mathematics. The sky is dark at night because the universe has not existed forever. The galaxies are drawing apart because the space between them is stretching. A faint microwave glow, the cooled light of the hot beginning, is falling on you from every direction at this moment, the same glow two engineers once tried to scrub out of their antenna. Countless neutrinos, ghostly and almost massless, are passing through your body every second and through the earth beneath you, as though neither were there. A wind of dark matter, whatever it is blowing through the room, unfelt, and the whole of it, the stars and the empty spaces, the black holes and the quantum flickers, the long expansion outward from a south pole of time, may have no edge anywhere, in any direction, at the beginning or the end. Trace the lines back toward the pole one last time. Every direction is the future. There is no south. There is no before. Just the globe, finite and whole and without a boundary, turning quietly in the dark,